All right, guys, let's go over this assignment. I broke it up into little pieces so I could explain each question and demonstrate stuff to you. Once we go over this, I do want to also show the one thing that we've talked about a couple times now is about 220 volt testing and using ground as part of that testing. Okay, that you can use ground, but if it's done a certain way, and I'll explain why and how that is. But let's take a look at this. And question number one is here. The temperature probe is in which two terminals on the board? So if you look, this is a picture that's on the back of the diagram. I have this diagram here, and let me just zoom out to show you where I got that. And I gave you a copy of that diagram too. 1 second. So it was on the first page of the diagram. You had two places you could go. Not all manufacturers are going to give you all this information. So sometimes you're just going to see this one picture here of the actual control board. All right? And then you would have to say, okay, where does this connect to the control board? Well, if we look here, this is pin number 1, that's pin number 15. So on a plug, whenever you're testing or looking at a wiring diagram, they're going to refer to which plug is that part connected to and what number terminal it's connected to, like 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 15. So the question was what plug and what terminal. But if we also look on this diagram here, they also had the connections of the control board showing that same plug here. And it said, the question was, the temperature probe is which two terminals on the board? So if we go back to this diagram here, if you look right here, the temperature probe is located on what two terminals?
12 and 13.
12 and 13. Now, that is okay because I didn't specify exactly. Because on some boards, you may have 5 different electrical connections to the board. Antoine. So I want to show you here, looking at this board right here. You just pick the whole thing up. So if you look at this board over here, this is that same plug that we're talking about on the board. But notice there's another plug on this board too. So if I've said pin 1 and 2, talking to someone over the phone, well, is it pin 1 and 2 on this plug, or is it pin 1 and 2 on that plug? You know, where exactly? So if you're talking to somebody and they want to know the exact pin location, you put it back up here. The exact pin location is, yes, it is number 12 and 13, and they tell you temperature probe is on 12 and 13, but the connector is P5, which was another question. So when you're talking about a plug and a connector, you're going to say P512, P513, not just 12 and 13. Okay, so P5 specifies the connector that it's on, and 12 and 13 is where on that connector are you going to, that is the most accurate way to identify it. Now, if we also go down here to the board, we can also, it's a little bit more complicated on this one, but we go to the schematic. Here we have the temperature probe right here, and a temperature probe goes to these 2 pins. Let me just bring it over here. A little bit too much here. But these 2, this is that plug P5. Notice they didn't put P5 on the actual diagram of the location, but they have 1 through 15. This is your temperature probe here, and it connects these 2 pins. That's what's happening. I put 2 fingers on there, and that's why. So pin 1, you could go 2, 3, 4, 5, 6, and get 12 and 13 here, or we could just count from 15 back. 15, 14, 13, 12, and we see that it's connected there. Yes, sir?
But in this case, it looks like a one block. Yeah.
Yes, it does. It's just a drawing.
Ah, okay.
Remember, schematics aren't actual pictures of the part. They are symbols or indications of how it connects to or where it connects to. So that, yeah, it looks like one plug, but if you look on the other picture, it's not, but isn't this one plug?
Yeah. Ah, okay. Yeah.
But if you look at it on the board, can you show that there?
Yeah, different levels.
Just pick it up and carry it over. So yes, it's showing one plug here, but if you look at the connector, it looks like two separate connectors. So, you know, again, just as long as you can sort of identify it. Now, the other thing is if you guys can look at the diagram, I know you all have a diagram somewhere. This one here is connected to the board, but one thing we don't have is the actual wire colors. Okay, if I didn't know what pin connector, that board is the two violet wires here. But if we look at this plug here, V4, violet number 4, and if we followed V4 down, notice they put V4 over here. So you could find V4 up there, and you don't have to like trace the line to find that wire. You just find this here, and this V4, it's the only place on the diagram that's going to have those V4s, violet wire. And here's the temperature probe there. So the answer is P512 and P513 for the first question. Okay? Any questions on that one?
No.
Okay. So this is the diagram, that's the probe. Let's go to the next question.
We need to specify the B as well? Or?
No. V is the color of the wire. Again, that's not in the schematic portion, it's in the pictorial. So those two diagrams side by side, if you ask that question, let me just bring that back up again. This diagram on the right is the same diagram on the left. If you had to troubleshoot a stove with this diagram, you'd probably pull your hair out and just say, what the heck's going on here? That's why they drew it like this, because it's easier to see the flow of electricity through the circuit. But they don't put the color wires and everything else because the more stuff you start adding on here, the harder it is to see the flow. Remember, electricity doesn't make curves, it just follows a line or a wire. This diagram is just showing you how this wire is connected to that point, and the schematic is saying, well, this wire runs over here and it goes through, there's 4 wires pinched together here, and that's what it's a black one. Let me see here. Like there's 4 wires here, and that's black number 3. This one here is black number 3. There's probably 2 down here, and black number 3 is here. So I got 1, 2, 3, 4, 5 wires connected together at one point. So if you look here, what we're looking for is these black wires, and this black wire here has 2 wires going down and 3 wires going up. So this exact point right here is that square dot right there. Okay? So again, learning to read a diagram, it's hard to take these straight lines and say, how do I follow it on here? You don't have to follow it. You just need to know one end of the wire is connected to this switch and the end of the wire is where the power comes in, or one end of the wire is connected to this element and the other end is connected to the board. You don't need to know every inch of the wire from one to the other, just the color of the wire and what parts it connects to. Yeah. Okay, so does that make sense?
Yeah.
Okay, so let's go back to this. How much voltage is going to the temperature probe? This one I put on the question. It's a little tricky because you can't find that answer on the diagram. Okay, there's usually 2 voltages that you'll find on boards that go to safeties or controls. It's usually 5 volts DC or 12 volts DC, okay? So what am I gonna do? Let's go ahead and just do a voltage test coming off the board. But I just did a Google search and it says operating voltage when connected to control board, the sensor circuit operates between 3 and 5 volts. And what happens when the sensor's connected? You get a slight voltage drop. So if the sensor wasn't connected, you'd have 1 voltage, but when current is flowing through, it's a slight voltage drop. That's the same thing like a water hose. When the water hose is connected and not running, it's under pressure. But once you open the hose, the pressure drops a little bit because of the flow of the water. It's not constant. You get that same thing in electricity. You get a slight little drop in pressure. So we're looking somewhere about 3 to 5 volts. How much voltage going to the probe? So we'll go back and check that at the end so that we're not going back and forth on every time, but I'll show you what to check, okay? Any questions on that one?
From 0.5 to 2 volts.
From 3 to 5 volts. Yes. Okay? Now, how much voltage does the control board need to operate? The stove itself has 240 volts. We have line 1 here, we have line 2 here, and we have neutral here. Now, if we look, and it's hard to tell in this picture, but we have line 1 comes in and goes to the board here at line 1. Now we have neutral come in and go to the board. Where is that on the board?
5.
That's 5, so that's P5-5, right?
Yeah.
1, 2, 3, 4, 5. It's the 5th pin. So let's look at this diagram again for one more second. There's nothing here showing you like where the transformer is on the board and that those 2 wires are power coming in for the board. But most boards will run off of 120 volts AC, even if the appliance is 240. Does that mean all boards are 120? No. But in residential appliances, not commercial, some control boards may have other voltages, but most of them only run off of 120 volts, even though this stove has 240. Okay, so there's a transformer in here that's going to step the voltage down and may have multiple voltages because the LED or the lights, like to tell you the clock, like 10 o'clock, those little lights, and when you press a button, the little light lights up. That's usually like 3 volts or very low voltage, could be 5. And then other components may have higher voltages up to 12. That transformer on the board will, this one right here. Can you get that right there? So this transformer right here is where power's coming in on white and black over here, line 1 here and neutral there. And then this transformer is getting that 120 volts coming in. And there's 4 little solder points at the top. That is the output voltages. And we'll do a voltage test on this at the end of the lecture, okay?
Then it receives 120, but to operate needs 5 to 12.
No. Well, yes. So most computers, even like the computer at your home, like a home PC, has a power supply that's 120 in the wall, but that power supply drops voltage for the computer components. Most control boards can't handle high voltage. Panasonic made a microwave, and I think this part's still sold today. It's called an inverter board. The main board, that's the clock and tells time cooked, 2 minutes and whatever, but then the inverter board took the place of the high voltage components in the transformer. In the microwave, like the transformer, the diode, the capacitor, and the magnetron, right? They run up to 4,000 volts. So this board took the place of 3 of those 4 parts, the transformer, the capacitor, and the diode. But that transformer, cap, and diode are what provide power to the magnetron. So they get 120 volt coming in, we get 2 voltages coming out, 3 volts, and we also get 2,000 to 4,000 volts coming off that board. Well, the biggest problem with the board is instead of running everything through wires, it's run through foil traces on the board, and high voltages sometimes, especially in high humidity areas, the voltage can arc through the air. So sometimes these boards fail just because of the voltage, and if someone's cooking for a long period of time, and let's say that microwave's over the stove and the lady's boiling potatoes or something and all this steam's coming up in there, that humidity could get on the board and cause a short on the actual board. Let me show you what that is. I know it's off of the stove, but let me show you what that board looks like. I'm sorry?
Say the heat from the cooking, the humidity, the heat from cooking stuff.
Well, like when you're boiling something on the stove and you might have something in the microwave, the boiling goes up into the microwave and the board's right there over the right front burner. That moisture can get inside and you get too much moisture on the board now to conduct electricity and we got a short. So if we look here, let me just... So the Panasonic inverter board, this is what one of that, there's a couple different versions of it. We'll take a look at this one here. So this is the Panasonic inverter. So we have the transformer here, we have diodes on the board, probably on the other side, we can't see them, but there's diodes and capacitors on it. I don't see them in that board. Let me see one other picture for a second. Let's see if this one has it. It depends on how they took pictures. That one's blocked. Let me see images real quick if I can find one. Oh, you can see it here. Okay, so in this diagram here, these are the capacitors. That might be the diodes. The diodes are usually black and they're soldered to the board. But this little plug right here is coming from the main control board. The main control board sends a signal here to tell it to power up. And then the 120 volts, well, that's the high voltage output. There's another plug. There's another plug here with 120 volts. I think this might be the high voltage coming off the board to the magnetron. This is a signal, and then there's some plugs right there. That might be the input voltage or vice versa. I don't know. So one is 120 and the other one is 4,000 coming off. And then this one here is very low voltage where one board tells the other board, hey, let's cook. And for this unit to turn itself on. Okay, let's get back to the stove that we were talking about. So in the answer to this question, 120 volts, and it's this L1 here, so it's on two different plugs. The line one's coming in on one plug, and the neutral's on another plug. Okay, they're not on the same plug. Now, which two terminals on the board supplies power? And here, L1 is one terminal, and P5-5 is the other. Not L2. L2 is just for the elements. So the answer to this one is L1 and P5-5, because this plug is P5, and 1, 2, 3, 4, 5, P5-5.
P55, P56.
No, sir. P5-5 and L1. The input voltage is over here. This, if you look at P56, what?
Yes.
If you look at P56, what does it control?
The motor.
What motor?
The lock mechanism.
What do you think the lock mechanism's for? What do you guys think? Why do we have a lock on in an oven?
For safety.
Safety.
Safety for what, though? You're not going to lock the door while you're baking, are you? It's not a microwave.
Machine safety.
Self-clean.
Self-clean.
When we want to self-clean the oven, we're getting 800 to 1,000 degrees. If there's grease in that oven, the idea of that heat is supposed to turn that grease to ashes, and then you just clean it right out when you're done. But if you open the door, two things could happen. Cold air will rush in, and if it hits that real hot grease, it'll immediately turn that grease to fire. Okay? And I had a student who was self-cleaning an oven, and somehow got the door open when it was off, but it was still too hot, and immediately flame and smoked out the whole classroom. We had to take it out. Luckily, the sensors in here only work off of heat, not smoke, so otherwise we would have had the sprinklers on in the whole building. But the other thing that could happen, not just the grease fire, is that if you open up the door and you have 800 degrees of air hitting you, that's worse than a sunburn. You'll get third-degree burns from excessive heat. That's why we lock the oven, for safety. You guys all set it for safety, but for safety during the self-clean cycle, not during any of the cooking cycles, okay? So, the next one, describe the F10 error code. So I already put it up here. I screenshot it from the diagram. What does the F10 error code say?
Runaway temperature.
So I asked you to give me a little more detail. What does that mean? Runaway temperature.
Oh, I need to know cooking cycles.
Just take a guess. What do you think it is?
Runaway temperature? And the temperature raise too much?
Yes. So most people, when they cook, especially baking, is about 350 degrees. In commercial, they run a convection oven close to 500 degrees. They want to sear the meat so that the juices stay inside, and they want to cook fast because, you know, they got customers coming in and they got to get the food on the table so they can turn over the kitchen. But in residential, we cook at about 350 degrees. And if you're baking at 350, and for some reason, let's say the sensor itself failed to tell the board the accurate temperature, it could go beyond. Or the sensor could be good. On the board, we have relays, and I'll point them out at the end. We have relays that when the oven reaches 350 degrees, the sensor tells the oven, hey, it's 350, and then the board will open up the relay, turning the element off. What if the relay got stuck? The relay got stuck, the element would keep heating, and it would run away, and the sensor would sense that it's doing. The sensor saying, hey, it's 350, the customer chose 350, shut the elements off, and the relays are supposed to do that. But what if a relay got stuck and didn't turn it off? The temperature would keep overheating, and the sensor is going to say, hey, I told you to stop at 350, it's at 500 now, it's running away from our set temperature, and that's what that means. Okay, so you can't automatically rule out a board, but most likely the board is what failed. But you need to check the sensor and see if the sensor's resistance matches the chart. And we'll talk about that in another slide here. Any questions about that? Okay, to the slide here. Okay. If the oven sensor was shorted, what error code would show up if the oven sensor was shorted?
F10.
F11.
F31.
F31.
Shorted oven sensor probe. Let's go back to the diagram because someone said F10 and another one said what?
11.
F11. So let's go to the diagram I have here. And we have the full chart here. F10 is runaway temperature. F11 shorted keypad or selector switch. Keypad is the touch panel on the control board. So we said oven sensor was shorted. And if you go to F31 down here, shorted oven sensor probe. Now you see this F30? Back in the day when they first came out with these control boards, it was just F3. Okay? On the double ovens that we have, the double wall ovens, one will say F3-1 and the other will say F3-2. What does that mean?
Wait, say again?
One says F3-1 and another code is F3-2. That would be for the upper oven is a -1 and the lower oven's a -2. So in other words, they gave you an F3 code and you have a double oven like we have in the kitchen there. Double ovens, how do you know which sensor they're telling you is bad? So -1 represents the upper oven and -2 would represent the lower. Now every manufacturer might do it slightly different. This is a single oven with a freestanding range, so they're not going to have those additional codes on this one. Okay, so a shorted oven sensor. So let's go back to the question here. So what resistance value would oven be if it was shorted?
0 or open line.
It would most likely be 0. An open line is not considered a short. It would just give you the F3 error. We'll go back to the code and look at it. Shorted means an oven sensor has a specific resistance value at a specific temperature. We have a chart for it here. If you look at this chart, room temperature is about 75 degrees. It's going to tell you it's 1,091 ohms plus or minus 5.3. So that could be 1,005.3 ohms, or it could be 994.7 ohms. Anywhere in that range would be good because you have to know the exact temperature. If it's 2 degrees warmer or higher, it's going to be slightly different. Now, one thing, Frigidaire did change their oven sensors about a couple years ago, not too long ago, and the resistance values are all about half the resistance that this chart is. So some people that don't look at the diagram and know the exact value based on the temperature could go to a newer Frigidaire range, and instead of it being 1,000, it only reads 500 ohms. And they're like, wait a minute. All the sensors I've ever tested are about 1,000 to 1,100 ohms, which is what that one is. And I'm only getting 500. My sensor's bad. And on the newer ovens, it's 500 ohms. So I did ask the trainer at the time, well, why'd you guys change something that's been working since the 80s or 90s when they came out with the electronic controls? And he says, we determined that the accuracy of the temperature in the oven was better with this sensor than with that sensor. So they changed that their oven temperatures are more accurate. Where the customer's baking, accuracy is very important for time. So when you're cooking steak, put it on broil and burn the heck out of it, we don't really worry about temperature, but when we're baking, we have to have specific temperatures. Okay? So number 8, what is the resistance of the oven probe at room temperature?
1080 to 11.
So right here is the answer right there, 1,091 ohms. Room temperature is about 75, 77 degrees. Right there was that, and that is on the chart, on the diagram. What is the resistance of the oven probe at 550 degrees? We can use that same chart at 550. What's the answer? 2,047 ohms. Any questions on those in the diagram? No? Okay. So let's go a little farther. Okay, identify the connector on the board that all sensor switches and power supplies connected to, and that would be what connector? P5. We said it earlier. That whole connector, again, here in the diagram it shows, it looks like 2, but the actual stove has a single plug on it. All right, let's talk about this because one of the students asked me about this, and I want to explain it a little more. And let me explain. Like on a washer timer chart, when you look at a washer timer chart, the black lines indicate when the switch and timer is closed. If there's no markings, it means the switch is open. So a lot of people are like, okay, so then this is when the switch is closed and the X must mean it's open, right? In this case, there was some wording down here, but it wasn't that clear. But in this case, the X's mean that is closed. So if I put it on bake or time bake, it shows L1 to bake. So line 1 coming in to bake. What does that mean? So if we're looking here at this diagram, L1 is going to bake. And I can't draw it on here. I'll do it on this one here. So if I put in bake, L1 has a relay going to bake. So power's coming in here and going back out to the bake element. That's what that means. So if we go back to the other one, L1 to broil also, right? So L1 also goes to broil. Well, right now, if you're baking a cake and you turn on the bake and the broil and you turn them on at the same time, you will burn the cake. It's so hot on the top. So they put a little indicator here. They put a little star right there. And I'll tell you what that star means in a minute. If it has a warming drawer, that motor is going to lock when you're cooking in the warming drawer. But let's take a look at something on this diagram. And what I'll point out is you guys have to look closely because you probably didn't even notice that asterisk there. And the notes on the diagram, and you guys had this whole diagram. I gave you a full diagram with the package. The star means it alternates with the bake element. That means the bake element comes on, the broil's not on. Now the bake's heating up the oven, shuts off, broil comes on, but only comes on for a very short period of time because we can't broil a cake. It would burn it. But we turn it on just for a little bit and then we turn it back off and go back to bake until we reach temperature and they both go off. But the broil being turned on a little bit helps even out the heat because when you're baking, the heat comes from the bottom element. And if you got, let's say, a cookie sheet this big, the bottom of that pan is going to get really, really hot, but the top of your cookies don't get that hot. So we add a little bit of heat with the broiling on the top so we get even heating on the top and the bottom of that unit. Okay? Any questions on that?
Then is just the connection between L1 and the
Now there is something here that's not identified. We got L1 to bake, L1 to broil, L1 to motor, door switch, and warmer drawer. There is one relay that is not listed on that board of electronic oven control relays. The manufacturer didn't put it there. Well, what am I talking about? Does anybody know what relay I'm talking about? Let's look at the diagram. We'll go back here first. Oh, no, I think we were on the diagram, right? Sorry. We go to the diagram. What relay are we talking about? I did say L1 to bake and L1 to broil, so there's two relays. Oops, I can't touch the board with two hands. There's two relays, L1 going to bake and L1 going to broil. Now, if we look at the board here, there's your bake and broil relay. There's another relay right here. It's not even drawn on the diagram. Can you take the camera here? If you guys look, this is your bake and broil relay, those two black relays at the top and bottom here. Bake being on the top, broil on the bottom, the same way they draw it. But look at that big black box right down here. All right? But if we look at the wires coming in, it's a red wire coming in and a red wire going back out. Okay, let's go back to the diagram. What does it say on the board? Line 2 what? In. And what does that say? Line 2 out. So in other words, line 2 is going into the board. It goes through that relay and back out. So what they did, and I'm going to go to my drawing here. I'm going to fast forward to a blank screen for a second. So you have it going to the board, and I'm just going to do this as a board. And there's two relays. Bake and broil. And this goes to the bake element, and this goes to the broil element. But hold on a second. So if I wanted to bake, I close that relay and I send power to the bake element. If I want to broil, I close this relay, send power to the broil element, right? Well, let's take a look at this diagram for a second. If we look, goes to the bake element, where does it go? Right back to the broil. I'm sorry, to the board on line 2. Both elements go back to the board on line 2. So if we go back to our drawing here, they both connect together and they both go back to the board to another relay which goes out line 2. Now, back in the I think I said 80s, but I think it might have been the 90s. No, it was the 80s, late 80s when they came out with the first oven control. Okay? EOC, you'll see it written all over your diagram, was electronic oven control. And when they first came out, they only had these two relays. But what happened was people would pull the element out of the oven, and this side went directly to line 2, so one of the wires on the back of the element had power all the time, even when you weren't using the oven. And if people weren't careful, they would pull the element out, say, I'll just pull the wires off, the oven's not turned on, and they would get shocked. So for safety reasons, they put a second relay. But that's not the only reason why they put a second relay. They put that second relay because if we turned on the bake, we have to turn on both of them so that power comes in and goes back out through the bake. But the thing is, what if this relay got stuck and we want to turn the oven off? This relay opening up will make sure both those elements don't come on. So you'll see this in a test, so you learn this, DLB. That's double line break, and it's usually on the line 2 side of the oven, DLB. So I'm going to give you a test, and it's going to say, what is DLB? So you guys know DLB is double line break relay, okay? So if you had a real old stove back from the late 80s to about the mid 90s or later, it may only have a bake and a broil relay to turn those elements off. They redesigned them for safety to add that additional relay on the other side of the element. This diagram here. Highlight the circuit of all energized components in the bake cycle. So in order to highlight the circuit, I'm going to go ahead and use a different color. We're going to come in. Oops, that's not what I want. We're going to come in, and we're going to go line 1 into the board. We're going to go out to bake. We're going to come back in, go through another relay, out line 2, and that's the element. Is that correct? Is that circuit correct? Yes? No?
Yeah. It's line 1 and line 2.
But is it complete? Does it answer the question, highlight the circuit of all energized components?
There's the ball element on energized fluid.
Your what?
The ball element.
Okay, so the broil element, we could add that too because it does alternate, but that's not complete. Because we didn't add what? We didn't add line neutral coming into the board, right? Because we have to feed the transformer on a board. Isn't that an active circuit right now? What about the oven temperature probe? Isn't that one energized right now? Because we have to have this probe working in order for the board to work. So all of these lines have to be highlighted. And the reason why I put those other lines in red is they're controlling different things. This red one is powering the board. This one here has the low voltage, and that's what's going to the oven sensor. Any questions on that one, guys? That is the complete answer. Both elements, the board power and the oven sensor, all of them have to be energized in the circuit.
Then, the temperature probe is a participant in all processes.
Yves, I'm sorry, I didn't hear. What did you say?
The temperature probe is a participant in all processes.
In any time you're using the oven, the temperature probe, this is how the probe works, okay? I give you a cup with water inside. I'm going to ask you, hey, is this water hot or cold? You stick your finger in there and you're going to say, oh, it's hot. No, it's cold. Well, your finger is the probe, your brain is the control board. How does the control board know it's hot? Because your finger told you. So the oven sensor is acting like your finger and the board's your brain. That's the sensor for your brain.
So we need to have the finger always.
You always have to have that on whenever you're using any of the elements because it needs to know all of the time when the oven's working what's going on inside the oven. What's the temperature? Okay?
Yeah.
So the next one. So now diagram 2. Highlight the circuits for the broil cycle. It's pretty much the same thing as the bake cycle, but we're not going to energize the bake element at all. So power's going to come in, go to the board, to the broil, go back out line 2, and out the unit. We have to put the neutral here, and we have to do the oven temperature probe. Basically the same thing as bake, we just don't turn the bake element on. We only use the broil element in this circuit.
This line 1 is involved there too.
Yeah, you need line 1 and line 2 for those elements for 240 volts.
The connection there.
Yes. Any questions on that one? No? Let's see if I can go to the last file without it crashing on me. So we go to the very last diagram. Highlight the circuit for the clean cycle. Now we have to look at this chart here, and the clean cycle shows bake is the only element that's on in that cycle. So it's very similar to the broil circuit. We just got to do the bake element. Power comes in, goes line 1 to bake. Out the DLB, neutral, and here. Am I done?
No. Why? Is baking. No, it's okay.
Yes, there's things missing. Let's go back.
No, clean cycle. No, you need to close the latch.
Okay, one second. You are correct. Let's look at this for a second.
Yeah.
So if we're in clean, this one's blocked, But unlocked and locking, locked, unlocking, that's a little misleading because this is the door latch, this is the warming drawer. So locked and unlocking, they're not showing you here. They're only showing you energize the motor for unlocking. So it's not explanatory enough, or I don't even know how to word it. It's not giving you enough information. But in order to self-clean, we said earlier, we have to lock the door for safety, right? Yeah. So if we go back to the diagram on this chart here, we have to send power to here. Am I complete now? Is the circuit complete? Yes? No?
It looks like.
No, it's not complete.
You have to go to neutral after that.
No, we have the neutral here.
And that's what you were just talking about, bro. The lock switch.
The lock switch? What about it?
You have to have that for the self-clean, right?
Yeah, if you look at this lock motor, can you get the camera? If you look at this piece here, the motor is underneath here, okay? But there's a little switch right there. And so when the motor locks, this little cam rotates and hits that switch. That's how the board knows, okay, the door locked. What if the door malfunctioned and didn't lock? Do you want to self-clean with the door being open? So as a safety, that switch tells the oven, hey, the door's locked, you can self-clean. So let's go here because there's even more to it than that. There's more on this diagram that you need to see. Okay, so right now, is that switch open or closed? It's open, so the door's not locked. But what if I had the door open in the oven and I pressed clean and told it to clean? It won't lock the door, will it? But will the motor run? No. Why not?
Because the door is open.
What?
The door is,
Okay, but how does it know that?
the door switch.
Ah, you see this switch here. This switch is closed right now. They're assuming the door is closed. Because if you look here, this is the light in the oven. When do we want the oven light to come on? When you open the door, right? When you open the door, the light's supposed to come on. Yes, there's another switch on top that we can turn on manually. But when you open the door, right now that switch is open. When you open the door, what does it do? It closes, turn that light on. But this one will open when that one closes. That's what they're showing you. The top one's closed, the bottom one not. When you open the door, top one opens and the bottom one closes. If this is not closed, which is this circuit right here, if that one's not closed, the board will not lock the oven door for clean. So if you went to someone's house and you pressed clean cycle and start, first thing that's going to pop up is the word door. It says, hey, door's not closed. And you say, yeah, but it's closed. Well, maybe your door switch is bad. See how that's an evidence of what's wrong with the machine? So this one being closed allows the motor, and then once the motor gets into the lock phase, it'll close this switch, and then the board will tell the elements to come on for clean. But almost like we did with the ice machine last night when we were working on it. The fuse went bad, but what caused the fuse to go bad? Well, it won't clean, or the elements won't come on if it don't lock. It won't lock if the door's not closed. If the door's closed and the lock locks, but the lock switch is not telling the board it's locked, it won't clean. So there's many things that can prevent the cleaning cycle from working, but we have to know, okay, what things are in the circuit. Was there any other information in this machine telling you about all them? No. This is where you as a student in the class have to know this is how this works and this is how that works. Is there any questions on this circuitry? I think that was the last diagram on that assignment.
Yeah.
You can stop the video. And I'm going to switch from AC to DC. Okay? And I'm going to stick the probe in the back of the plug. And I'm going to go ahead and turn it on, plug it in and see if I'm in far enough to get a reading. And I'm going to press bake, can's clear, bake, 350. Oh, wait. That was time bake. Let's see here. Bake. 350 and start. Oh. Okay, so now we're getting 2.3 volts. So it's only about 3 volts going to that sensor. It's probably about 3, where the Google said 3 to 5. Most of these run more like about 5 volts. It could be a voltage drop from the resistor. Remember I told you voltage when it's off is higher than voltage when current's flowing through. You always have a little bit of a voltage drop on any electrical circuit when the circuit's running. If you get too high of a voltage drop, it won't work right. So if I cancel the oven, the voltage is dropped to about 1 volt. Now it's even going less, so it has no voltage when it's off. Why is it important to know the voltage to the sensor?
You know, except
Besides, the sensor is working.
exact voltage in the sensor.
Well, you don't know if the sensor's working. You go into someone's house and the oven's not working, and you get an F3 error code. Well, an F3 error code means something's wrong with the sensor, okay? And we can go back to the chart that we talked about and says, hey, at room temperature, that sensor's supposed to read 1,091 ohms. You could ohm out the sensor. What if you got an F3, you ohm out the sensor, and it gives you 1,091 ohms? That means your sensor's good, right? What if the board is bad? What if there's something wrong with the board and it can't see the sensor? Well, if you don't have the voltage coming off the board, then the board won't pass through the sensor and it won't work. So this is a way of knowing, okay, is my problem really the sensor, or is my problem the board not being able to read the sensor? Like I have a battery in my meter and that's what's telling me the voltage or whatever. Well, is the board, like having that battery, sending the voltage through that sensor? So you could have a bad sensor 9 out of 10 times. F3 is sensor itself's bad. It happens a lot on ovens that are self-clean because that sensor's put on to almost 1,000 degrees in self-clean, 850 to 1,000 degrees. The sensors fail a lot at extreme temperatures. But in this case here, if you had the voltage coming off, you have to assume that the board is doing what it's supposed to be doing. You could have a broken wire in that circuit. So what you could also do, we unplug this plug from the board like this, and now I can go from ohms oops, I got a reflection of the thing. And I'm on kilo ohms and I'm getting 1,113 because we did turn the oven on for just a little bit, so it's probably starting to warm up. But I'm testing the sensor from the board. I'm not at the sensor, which is, where's the two purple, oh, right here, this plug right here behind these wires. This is the purple wires coming from up here, right here. This is the oven sensor. Watch the reading here on the meter when I unplug it. Ready? You guys see the reading on the meter? When I unplug it, what happens? It's sent to open line, right? So in other words, the sensor could be good. You could have an electrical connection between the board and the sensor. So testing from here, and I get a good resistance, I can test my sensor from the board. If it's a wall oven, the sensor may not be easy to get to the plug back here to check it. It could be behind the oven and the whole oven has to come out. But you could take the control board off of the oven and test the sensor from the board. What other things could I test from the board here? Let's clear this for a second. Now look at this diagram here. I checked the temperature probe just now. What else could I check from the board? Can I check the door switch? Okay, so in this case, the door switch is in the front of the oven, and I'd have to lift the whole top up just to check it. But I can go over here and check the door switch from what? These two pits right here, which are the two right next to the temperature probe. That's going to be this orange and pink one.
9 and 10. 9. No.
The orange and pink. Okay. I'm getting an open line, right? I might not be in there reading good enough. I think, let me see something. I got 2 wires, then I got, okay, no, it's this one. I was in the wrong 2. It's the gray and pink, and gray and orange. Sorry. I'm still not reading, am I? Right? Okay, so let's try something here. I want to put this plug back on. I'm going to plug the machine in. I'm going to clear it out. Bake, 350, start. Well, that's the timer. But bake 350. And that's working, right? Let's clear it. Let's go to the clean cycle. Now you got to set how many hours you want to clean. It's usually 2 to 3 hours, okay? Now if we wait a few seconds, it goes into clean. And what's it saying here? Door's locked, huh? And the lock mechanism's working. And it shouldn't be if it's not reading the door switch properly. So we'll have to check that out. Because I'm not getting a reading from the board. Maybe I wasn't plugged all the way in that plug correctly.
And you can open the door now.
I can cancel it right now, but if I go over 550 degrees, I can't open it now. If I go over 550 degrees, and I'll show you guys here, watch the cam when I cancel the cycle. Watch the motor unlock the door. And you can see as it rotates, and watch and listen for the click of that switch. Just listen. Listen what things are doing. Listen when the switch is activated, deactivated, whatever.
Yeah.
You heard it click?
Yeah.
So that's the signal to tell the machine, hey, the door's unlocked, all right? Now the door switch, well, let me go ahead and just unplug this one more time. Maybe from the backside I didn't get it. I don't want you guys sticking the meters leads in here unless you have the computer probes. They're real thin. They go on the end of your meter lead. And I'll show you the kit on Amazon you can buy to attach so you can get in there. But if you look here, you could see metal prongs here, so I could touch the face here and get a reading. So we're going to try that. Because like I said, maybe I didn't have it in good enough in that unit. But again, if I check this gray one and this orange one, I want to check first my meter's working. Okay, my meter's working. I get a reading when I open and close it. So I'm going to check the gray and orange. I'm going to touch them right here. Like this. And I didn't get a reading. There we go. That might be the door switch. Let me see. Might be the 2 outside ones. This diagram may not be 100% this stove. So I can't, Jonathan, go over and open the door for me when I ask you to. I may have been on the wrong 2 terminals, but I hold on a second. I can't hold this and that one at the same time. Okay, go ahead and open the door. It says OL, close the door. But you can see I can check the door switch right from here. I don't have to go right to the door switch. Now if I don't get a reading, does that mean the door switch is bad? Then what does it mean?
No, it means the connection could be faulty.
You could have a broken wire between the 2 as well. So if you don't get a reading, that's just an indication, hey, I have to go to the switch and check the switch itself. Now the reason why I don't want you to stick these in the opening here is the opening's smaller than your probe on your meter lead, and it'll expand the plastic. The plastics don't matter. What matters is the electrical terminal inside. If you expand that too much, when you plug it back onto the board, when you plug it, it's too big and it doesn't make connection now. Okay? So that's that sensor. So we could check out the lock motor. We can check out other components right here from the board. Now, I want to do something. Where was that tool that we put the wires on? Here, hold on.
Also,
Where's the blue one?
the elements, you can check from there as well. The elements.
Yes, you could. But on this stove, it's easier just to go right to the element.
The blue one.
Huh? No, I want to do something here.
You wanna do the activity with the neutral? The ground?
One second. Don't try to get ahead of me. I'll explain what I'm doing in a second. Let me just reconnect this. You can just set that on the ground there so that, and just aim it right at what I'm doing. Stupid paper. All right. So what did I just do, guys? What did I do?
Cut the cable.
I didn't cut the cable. I disconnected what? What did I disconnect?
The black.
The black is what? Black is what? Black is line 1. Okay, so here's the thing. I don't want to leave these wires where they can touch anything or touch me. So I'm going to use a little tape, normally electrical, but as long as I got this tape, and I want to leave these exposed for a minute because I want to show you guys something. And this will work anywhere in a 240 volt circuit. This is where when people tell me, oh yeah, I'm on a 240 volt circuit and I checked everything to ground. Okay, well, if I'm checking the ground on a 240 volt circuit, what voltage reading should I get?
120.
120, because neutral to any line is 120, correct? So watch this. I'm gonna go ahead and plug this stove on. I gotta be careful not to touch those wires. So you guys at home, don't do what I do what I say. But let's go ahead and let's check. I'm going to voltage. I'm gonna be on AC volts. Can you see the meter in the camera? You can actually see what it reads? Okay, so I'm not turning anything on right now. I'm just gonna go ahead and check line 1 to ground. And I got 120.7. Well, actually line 2, and this is line 1, 119.7. So I have voltage on both lines, right? Okay, well, right now, I'm not gonna have any voltage here. Why? Look at the diagram here for a second. When I took off line 2 here, or line 1 here, okay? Line 1 has to go through one relay and then another relay to get line 2. So I'm never gonna have voltage on that line 1. But let's just say that relay and that relay are closed. Let's just say this relay is closed and line 1 to bake is closed. Those two relays are closed. That's gonna give me a 120 volt reading. I can't do it on this circuit with those two relays on the board, but let's go ahead and check the stove out, okay? Let's look at the top of the stove. Let's look at this burner here right at the top of the stove. I'm gonna go ahead and turn on a single burner. So I'm gonna turn on the one of the burners, okay? Let me just make sure it's heating up. No, I'm not getting any heat on that one. Oh,
Yeah, but like.
I'm not getting any heat, why? Line 1's disconnected. Okay, that's good. So my element's not working, right? I'm gonna go to the switch now because the light's telling me, hey, there's power there, right? So I'm gonna go to the switch and I'm going to check line 2. Let me put my meter here. I'm gonna check line 2 to ground. What do I got?
120.
Okay, but line 1's disconnected, right? So what if I check line 1 to ground? How am I getting 120? There's nothing even connected to line 1 on the back of the stove. Because it feeds through the entire circuit. In other words, if we look at this diagram here, if I took line 1 off here, I disconnected this line, there's no line coming in. Line 2, if these switches are all closed, line 2 will come all the way up to here on the switch. It feeds through the element. It's potential voltage. It's not current flow. So the element's not going to work because there's got to be a path for the current to flow in and out. But if you have a break in the circuit, it doesn't matter where it's broken. Okay? If I took the wire off the element, I'm going to have 120 no matter where I am in the circuit. Let's take a look at that. Okay, I'm going to put this back together again. Give me a second here to wire it back up. Remember, I unplugged it before I stuck my hand in here, right? I'm going to take off this orange wire off the bake element. Oh, I want to tape it up. Give me a second here, guys. Now, I want to leave this element wire off exposed. Normally I would tape it up so it doesn't touch anything, but I want to show you a test. One side of the bake element's off, right? There's a break in that electrical circuit. The element will not get hot if the wire's not connected, right? But what if I plug it in? Take my meter here, and I'll press bake. Oh, now the element's getting hot. My clock's not working. Oh, my board's not connected. That would help, right? Shouldn't do it while it's live, but. Bake, 350, 3, 2, 1. Listen to relays. So the relay is accepting your command. Listen to that. That means your touch panel's working, the board's trying to turn the element on, right? Now, if I go to this element, it's not going to get hot, but let's see something. Can you go over this way a little bit? So if I check voltage to this element, what am I going to get?
120.
Well, to the element itself. What does my meter read? 0, right? But if I touch this wire, which is coming from the board, and I touch ground, what do I get? What if I touch that one to ground?
Same key.
120. But what if I touch this wire to ground? Anywhere in the circuit I touch a 240 volt circuit, I'm going to get 120. It doesn't tell me where the break is. Now what tells me where the break is I go here and here, and my meter will read 0 volts, right? But this was the orange wire, but let me take this meter, instead of touching that wire, let me go to the orange wire here, right here. And I touch here, what do I got? 220, right? 209. And then I go down here to this element, what do I got? 0. So that's telling me the wire here is not bringing the 200 volts down there. That's how you got to check a 240 volt circuit. One meter lead has to be all on line 1, and the other meter lead has to be all on line 2 to find the problem. Because if I touch this thing to ground,
120.
I'm going to get 120, but the circuit's open. There's no wire going to it. You cannot do a 240 volt circuit to ground. But if I disconnected it, I could trace one circuit back to ground now. And I could trace this circuit back to ground. But don't do it that way. I don't want to explain why it would work that way by disconnecting one side of the element. But don't ever do 220 to ground because you'll never find the answer. Okay? Any questions on that? No? Any questions on anything that we covered tonight?
You see, don't ever do 240 or 220 to ground.
220, 240, 440, any high voltage to ground. That circuit has more than one line of power. Each one to ground is 120. Okay. So when they're together, they make 240. So if you're checking any one of those wires to ground, you're going to get 220, even if a switch is broken and open.
There is a hazard.
Yes. All right, guys.
The square, right?
Yeah.